Lab TV travels to NAVSEA Carderock in Bethesda, Maryland, to meet an engineer who uses computers to help design ships for the Navy.
Someone comes up with an idea. They start thinking about what they want the ship to do, how fast do we want it to go, how quickly do we want it to turn, how far do we want it to go, what do we want it to do when it gets there.
Whether it's a cruiser, an unmanned vessel, or a submarine, the purpose of the ship determines what it should look like.
For instance, an aircraft carrier, you see the shape of the ship is dictated by what it's supposed to do.
Some ships need to go fast. Others need to carry heavy loads. But no matter what the job is, the design has to be safe and smart and not waste energy. It starts with a computer drawing.
We generally get what we call a CAD drawing, so that's a computer-aided design. It's a 3D design of the shape of the ship. Designers these days, rather than drawing things on paper, they actually draw it in the computer.
Susan can take the 3D computer drawing and run lots of tests on the ship design using a program called CFD.
Computational fluid dynamics, or CFD as we call it, is a computer program that models the physics of the fluid flows as they interact with the surfaces of the ship.
Using CFD, Susan can examine the fluids, either air or water, as they flow over the ship. When a ship moves through these fluids, it experiences a force called resistance or drag. To move the ship forward, the drag must be overcome by a force called thrust.
As a hard surface moves through the water itself is kind of sticky. We call that viscosity. And that stickiness creates a certain pull on the ship that resists the ship from moving through the water. And so one of the biggest concerns in designing ships is how do we minimize that resistance, minimize that stickiness that we see between the water and the hull of the ship itself.
This underwater vehicle is designed to rescue sailors so they can safely get out of a disabled submarine. Susan recreates the flow of water over the surfaces so she can study the resistance.
In fluids, what we tend to look at are streamlines. So the streamlines show us how the fluid moves over the surface. We can see the fluid flows pretty smoothly over the top and over the bottom, but when it gets into this region here, it creates a lot of turbulence and drag. For this particular vehicle, we're not as concerned with its efficiency through the water as we are with how safely this region here stays stuck onto the submarine.
Susan studies the forces between the rescue vehicle and the hatch of the submarine to make sure drag on the pipes and propellers won't pull the vehicle off the sub. Sometimes she studies wind, not water, like with these two huge cargo ships.
So what we're looking at is the wind as it blows across the ocean and hits the ship here. And this ship acts as just a giant wall. When the wind blows across it, it tends to make the wind separate. So it separates off the back and creates what we call a cavity or recirculation area here. So it gets all churned up behind here. And one of the things we're really concerned about is how does the wind blowing off of the ship affect the ship in the background.
Susan can make small changes in the design, analyze the fluid flows, and keep improving the ship.
I mean, ideally you want the ship to go through the water completely silently with as little wake as possible and as efficiently as possible. That's the ultimate goal. How close we get to it is always the challenge. And
for Susan, that challenge is a lot of fun.
In high school and in middle school, I was always very interested in science. And so I eventually decided, you know, what would make me happy doing 24 hours a day or 12 hours a day, and I want to get up the next day and do it again, and it's the science.
Check out Lab TV Online next week for part 2 of Ship Shape to see how the computer designs become real ship models.